Hello all, I am Yugender Reddy Bangala, part of Study Group 6, along with my teammates Nikita Kancharla and Venkatayappa Reddy. The learning of Study Group 6 from three articles Dr. Day assigned for reading will be presented in this presentation. Papers assigned to read were Computing Machinery and Intelligence by Turing Alon and Hoagland, Machine Learning in Python by Sebastian Joshua Patterson and Nolet, Benchmarking Contemporary Deep Learning, Hardware and Frameworks by Dai and Daniel. I am going to explain about the paper Computing Machinery and Intelligence by Turing Alon and Hugland, and other papers will be explained by my teammates. The question, can machines think, is addressed in Turing's paper. By determining whether or not a hypothetical digital computer can play the imitation game and convince the interrogator that it is a human. Turing has explained with an example of a game called imitation game. Three players would participate in the game. All the players will be invisible to each other. The other two participants will be interrogated by the interrogator. The questions will be of yes or no type, which a computer can answer. Answers to questions will be typed, so there will be no indication from written response whether the reply is a computer or a man. The interrogator will decide which player is machine based on the answers to the questions. The game will be played multiple times with players, changing the players. The interrogator will decide which player is a machine based on the answers to the questions. Human A high number of wrong interrogator selections of which player is computer indicates that a digital computer may impersonate people without being recognized by humans. Turing A high number of wrong interrogator selections of which player is the computer indicates that a digital computer may impersonate people without being recognized by humans. Turing explains that any digital computer that can be imagined is a possible competitor in the imitation game. A digital computer has three parts: store, where the data and instructions are stored; executive unit, which performs calculating operations; and the control, which ensures that instructions are executed correctly and in the correct order. Turing proposes that the game's computer be a universally imaginable digital computer. A universal computer is a single computer that can be designed to execute a variety of jobs. It is a single computer with many functions and uses. Turing concluded that a universally possible digital computer could play the imitation game if it is have enough storage, speed, and programmed instructions. The following were additional problems with Turing's approach. Computers do not make mistakes. Each programmed process performs the same way every time, but the human makes errors. Computers can think for themselves. They only do what they have been programmed to do. Humans have the ability to create the new one every time. Computers are discrete state, whereas the humans are continuous. Computers do not have a soul, and thinking is a function of one's soul. Because man is superior, computers will never be able to compete with people. Computers have limitations. They cannot answer some issues that only humans can. Computers lack feelings, the ability to differentiate right from wrong, initiative or creativity, and thus are enabled to perform some human linked tasks. It's impossible to construct a rule set for what a man should do in every situation. Humans don't respond the same way in every situation, whereas computers do. Extrasensory perception may be present in human players. Hence, game results will not be representative of average human behavior. Turing examined the flaws in each proposed argument against Turing's concept functioning in the paper. He came to the conclusion that these arguments were unsound and that his proposed solution to the problem is correct. Thank you. The other two papers will be explained by my teammates.
Coming to the paper 2, machine learning in Python, it explains about main developments and technology trends in data science, machine learning, and artificial intelligence. It has written by Sebastian Raska, Joshua Patterson, and Corey Nolet. So coming to machine learning, it's a branch of artificial intelligence that allows computers to learn without having to be explicitly programmed. Here, machine learning is concerned with the creation of computer programs which adapts a new data. So actually, like a main modules has been built by the Python community to assist programmers in implementing machine learning. So yeah, here we have different types of machine learning. Coming to the classical machine learning, it as a deep learning, which is a subfield of machine learning which focuses on a DNA parameterization. For clarity here, a non-deep learning based machine learning is a classical machine learning. Okay, sir, stop Jaya, please, sorry. Coming to classical machine learning, deep learning is a subfield of machine learning that focuses on a DNA parameterization. For clear to explain, non-deep learning based machine language is machine learning is a classical machine learning, whereas machine learning is a catch-all phrase for both deep learning and classical learning. Here we have 4 types of which is skate-run, which is Python's most useful and robust machine learning package, and addressing class imbalance is here, like algorithms may learn to predict the majority, label the majority of the time to optimize the training objective. Class imbalances can lead to large prediction bias. Coming to assemble techniques, which mix a number of machine learning algorithms or models, are often used to improve model performance, provide stability, and reduce bias variance trade-off. Coming to scalable distributed machine learning, task machine learning provides distributed implementation of classical learns machine learning algorithms, as well as Skycat learn compatible API. Here, coming to Dask ML uses multiprocessing, which has an advantage of spreading algorithm calculations over several nodes in a computer cluster. Coming to next slide. Coming to next one, automatic machine learning. It's automatic. We have tools seek to automate one or more phases of this machine learning pipelines, making it easier for non-experts to develop machine learning models while eliminating repetitive chores and allowing seasoned machine learning professionals to build better models quickly. As we have a number of researchers and creative methods to automatic machine learning growth, it will extend over a variety of learning objectives. Therefore, it is critically that the community establish a consistent mechanism for comparing them. Here we have 3 primary parts of machine learning pipeline that can be automated. There are data preparation and feature engineering, which cleanses the data, mapping individual fields to data types in preparation for feature engineering, and imputing missing values are all come under common data preparation steps in machine learning pipelines. Next one is a hyperparameter optimization and a model evaluation. The fields are frequently modified during the feature extraction step to produce new features with a better signal to noise ratios, or to scale features to help optimization algorithms. Here are feature normalization and scaling, encoding features into one hot or other format, and it produces polynomial feature combining combination of all common features extraction approaches. So feature extraction also used to minimize dimensionality by decolorating and reducing the number of features. Yeah, using a technique such as principal component analysis, random projections, linear discriminant analysis, and decision trees. Here, the strategies have the ability to improve the features discriminative powers while reasoning the consequences of the dimensionality curves. The third part of this machine learning pipeline is neural architecture search. So based on neural network topologies, have the neural search spaces may be classified into, it's a classified into four categories. One is complete structure, which creates the complete network from the ground up by selecting and chaining together a collection of primitive, and a cell based one which looks for the combination of a certain number of handcrafted building components known as cells. So the one is hierarchical, which extends the cell-based techniques by introducing many levels and chaining together a certain number of cells, iteratively constructing the higher layers using the primitives described in lower layers. Other one is a morphism-based structure, which transfers information from previously successful network to a new one. Coming to other one, GPU accelerated data science and machine learning. Here, scientists have been using GPU's potential for boosting highly parallelizable calculations. It was first introduced in 1999. However, it wasn't until the of CUDA in 2007 that general purpose CPU computing gained traction. Here we have a general purpose of GPU computing for machine learning as described in 5 features. So there are a general purpose GPU computing for machine learning, which has high speed memory spanning numerous multiprocessors, each containing several parallel cores. GPUs allow the single instruction multiple thread programming paradigm, but a better throughput and a more parallel model than SIMD threads. Here, the additional thing is that the core can share memory with other cores in the same multiprocessor. Coming to end-to-end data science rapids. Here, Rapids is an open source project aimed at fostering and expanding the ecosystem of GPU, accelerator, Python tools for data science, machine learning, and scientific computing. Rapids complements current libraries, addresses gaps by offering open source libraries with critical components that the Python community lacks and fosters ecosystem. Coming to anti-array and vectorized operation. Here, Python may invoke a BLAS implementation to improve SIMD operation, although its ability to vectorize functions is restricted, which results in little to no performance gains. Just-in-time compilation is supported by the Numba library, allowing vectorized routines to take advantage of technologies like SSC and Altivec. Coming to other feature is like interoperability. In the past, the necessity to duplicate a data set or dramatically alter its format each time a new library was used was a barrier to interoperability. As a result, zero copy operations are frequently favored, which are operations that do not involve copying data from one memory region to another. So this is specifically true for GPU libraries because these transfers and translations need CPU to GPU communication, negating the benefit of GPU's high-speed memory. Here, classical, coming to feature for classical machine learning on GPUs, is having a numerous kinds of specialized algorithms. The landscape of GPU accelerated machine learning packages for Python is very fragmented. Coming to distributed data science and machine learning on GPUs. Here, GPUs have become an important part of general purpose scientific computing because of their great performance and flexibility. Despite the fact that GPUs have capabilities like a high-speed memory bandwidth, shared memory, extreme parallelism, and consolidating, whether it's read or write to global memory. The amount of memory accessible on a single device which is limited compared to the host memory. Coming to the other part, deep learning, which is a type in machine learning. Here, like when we using the classical machine learning, the prediction performance is heavily reliant on the data processing and feature engineering, which creates two data set that will be used to train the models. While certain deep learning algorithms may take data as an input, the vast majority of state-of-the-art approaches for determining the best predictive performance or a general purpose and capable of extracting significant information from raw data in a semi-automated manner. Here, their optimization job and modeling architecture includes automated feature extraction as a core component. Here we have four types of static data flow graphs. One is dynamic graph libraries with eager execution where users may engage with the computations in real time through dynamic computation graphs, which is useful for implementing or creating new deep learning algorithms and architectures. While this trait is liberating, hashed execution comes with a significant computational cost. Other flow graph is JIT and computational efficiency. All of dynamic graph libraries discussed about accomplish the appropriate degree of computing efficiency by offering predefined building blocks for specific neural network components and deep learning algorithms, despite being favored by economists due of their simplicity of use. Coming to deep learning APIs, it is for like a several wrapper libraries sit on top of deep learning libraries outlined in making deep learning more accessible to the practitioners. And other part of static data flow graph is new algorithms for accelerating large scale deep learning. Here, algorithmic developments lately focused on approximation approaches for optimization algorithms, among other things, to increase the scalability and performance of deep learning through improved software implementations. Coming to explainability, interoperability, and fairness of machine learning models, explainability is the ability to comprehend, whereas interoperability is a capacity to see impact of changes in the input or parameters on a project outcomes. Here we have 6 features so comes under this. So first one is the feature importance, which shows it's a linear connection between the inputs, learning weight parameters, and outputs is what makes linear models so appealing, because these models may naturally weight the importance of each feature, and the inputs or learned parameter has a predictable effect on the outputs. They are typically implicitly interoperable. However, because numerous characters has a varying correlations determining the independent attribution, each feature has on final prediction can be difficult. There are many different types of feature significance, but the basic idea is to make the parameters and features easier to understand. The actual qualities of a resultant feature importance might change depending on the purpose based on this description. Constraining non-linear models. In a linear models, putting restrictions on the objective function is a popular way to improve the consequently the interoperability of the learned parameters. Coming to logic and reasoning one, in the decision trees, feature importance scores are frequently derived using the information gain and impurity criteria, allowing spreads with a greatest influence on the prediction to be preserved closer to the tree's root, because they already include the information needed for interpretation. Decision trees are referred to as white box models. So this is also extend this notion by extracting logical formula from tree assembles by integrating learned split predicts along pathways from the root to predictions at the leaves into logical conjunctions and all paths for a class into logical disjunction. This logical formula may evaluate using logical reasoning techniques to get insight into decision making process, allowing models to fine tune to eliminate inconsistencies and enforce particular rules. Coming to explaining with the interactive visualizations. Visualizing the properties of a model's learned parameters and interpretation of its interactions with a collection of data is frequently beneficial here. Coming to privacy, which is more important, the implicit nature of such data is dangerous since it can infringe on a user's privacy and exploited for nefarious reasons. Fairness indicates apply commonly used metrics for detecting fairness bias, such as false negative and false positive rates to various slices of data set. Final type of machine learning is adversarial learning. Adversarial learning is closely connected to explainability in that it necessitates the examination of a trained model learned parameters in order to better comprehend the impact of feature mappings and decision limits on a model security. Finally, the conclusion of this article is reviewed most of the uh, notable advances in machine learning, data science, and scientific computing. It provides brief background into a major topic while investigating the various challenges, current state of solution for each. Python has emerged into it using several research and application domains that we highlighted in this study due to its ease of learning and usage. Here, we expect Python to remain the dominating language for scientific computers for many years to come, thanks to breakthroughs in CPU and GPU processing, as well as ever-growing user groups and ecosystems of libraries.
Yeah, hi everyone. I'm Venkat Ayyappa Reddy. Here I'm going to discuss about benchmarking contemporary deep learning hardware and frameworks. Benchmark is a technique of comparing tools to determine the best performing technology in the industry in machine learning. However, given to the enormous number of elements that go into the tool's success, comparing multiple machine learning platforms can be complicated. Here, all these topics are involved in the benchmarking. And next, I'm going to discuss about GPU. GPU is nothing but a general processing unit. GPU can process large data at once, making them ideal for machine learning, video editing, and gaming. GPU can build into computer CPU or solid as a separate piece of hardware. A GPU is made up of render high resolution graphics and video in real time. GPU are often employed for non-graphical applications such as machine learning and scientific computation, since they are executed parallel operations on several sets of data. A GPU is a type of processor that executes at doing specialized calculations. In contrast, the central processing unit CPU exceeds the performing board of computations. The majority of computations done on the gadgets we use every day are performed by the CPU. The GPU is capable of executing tasks faster than CPU. When it comes to playing certain types of games, The GPU is very crucial element for the gaming system and many scenarios even more important than CPU. Similar explanation, a graphic processing unit GPU is single chip processor that manages and improves video and graphic performances. And here we can see the difference between a CPU and GPU. And CPU are processors that supports advanced logic and serial operations. This is mirrored on the design with a few cores. Here we can see in the CPU there are only 4 cores of ALUs, but in the GPU we can see a multiple cores. GPU on the other hand have hundreds of smaller cores for simple computing, resulting it's a better throughout the CPU. CUDA abstracts GPU's numerous cores into blocks, allowing it to access them. Each block can have up to 512 threads available, with a total of 65,535 blocks possible to run at the same time. Every thread runs a brief program with added benefits of being able to operate in parallel with other threads. TensorFlow is implemented in the CPU and GPU. TensorFlow uses this method to increase processing power by executing threads to thousands of threads at the same time. Coming to FPGA, FPGA is nothing but a field programmable gate array. FPGA is a customizable hardware device. It contains the logic gates. FPGA are designed to reprogram the logic gates. It is designed by using a hardware description language such as Verilog and VHDL. The program dictates which connections are made, how they are implemented using digital components. Application specific integrated circuits are nothing but ASICs or processors are particularly well suited for FPGA prototype. An FPGA can be programmable until the ASIC or processor design is finalized. At the point of finalized ASIC can be manufactured. FPGA are used by the Intel to design new chips. FPGAs are 3 to 4 times faster than GPUs. FPGA can handle 233 images per second with a device power of 25 watts. FPGAs are easy to spot, look for an oversized Arduino. Coming to ASICs. ASICs are nothing but application-specific integrated circuits. ASICs are chips that are developed and manufactured for the specific task and specific operation. ASICs are permanent and cannot be modified, and unlike FPGAs. FPGAs are reprogrammable but not ASICs. Particularly compared to the FPGAs, ASICs are high efficiency and power and performance. ASICs are now being developed in large number to support artificial intelligence and related technologies. Google-owned TPUs and tensor processing units are basically a collection of ASICs intended for machine learning and optimized to run open source deep learning software. Other technique gains such as FIJUs, DLU is nothing but deep learning unit, are pursuing similar inactivities. Google TPU is a good example to consider when thinking about how an AIC can be used to address very specific and narrow functions and handle the workload in a parallel manner. Researchers are confirmed that TPU 1.0 has about 15 to 30 times speed up compared to CPU and GPU based on the ASIC technologies. Enhanced hardware performance. Here, like despite the fact that numerous cores, CPUs and threading are commonplace, they nevertheless have flaws in the big data era. Deep learning models, for example, usually containing products and matrix transpositions, residues, and composition resources, because this specialized chipset contains numerous cores on chip memory. GPUs, FPGAs, and ASICs have better computational performance and lower latency than regular CPUs. Based on the performance, CPU benchmarks hierarchy ranks all current and previous generations Intel and AMD processors, include all best CPUs for gaming. CPU has a significant impact on overall performance, and it is considered by many to be most crucial components of computer. However, when it comes to time to buy CPU for your desktop, you'll be faced an bewildering array of modeling numbers and specifications of both Intel and AMD's. Deep learning frameworks. Uh, Through a high-level programming interface, deep learning frameworks provides building blocks for designing, training, and validating deep neural networks. Engineers and scientists can use open source deep learning frameworks to design activation functions, create innovation algorithms, train massive data, and deploy neural networks on variety of hardware platforms, including servers and mobile devices. We divided 18 frameworks into three categories: mature frameworks, expanding frameworks, and inactive frameworks based on the wide range of usages. Support teams programming interfaces. Then 10 mature frameworks can be deployed right now to speed up training, improve scalability, and reduce deployment risks. Although developing frameworks are not widely used in the industries and research activities, some of them may be useful in specific domain. Retired frameworks are mostly inactive. Deep learning is one of the hottest topic in machine learning, with DL approaches outperforming state-of-the-art outcomes in the challenge domains like image processing and natural language processing. Several open sources frameworks appended to the support the growth of DL by providing implementations of most common DL algorithms. The algorithms supported by these frameworks and quality of their implementation differ. The goal of the study is to compare three of the most popular comprehensive data learning frameworks. Those are just nothing but Google TensorFlow and Microsoft CNTK on quantitative levels. Uh, Dedicated application programming interface for hardware devices, abstract complex parallel development and improvement executive performance, and all provided by the specific programming libraries. The NUVDIE and CUDNN libraries, for example, can improve the performance of Apache, MXNet, and Kefi on of NVIDIA GPUs. Mainstream deep learning frameworks. The world as we know it is being transferred from machine learning. New thoughts and emerge as organizations continue to explore further into the potential of viral intelligence. Deep learning is a very important area of research. Deep learning is a subset of machine learning that can improve accuracy and efficiency in the AI world. Deep learning algorithms that have been trained properly can be rival, if not outperform, human cognition. Over last few years, data scientists, researchers in the area of deep learning have been deploying frameworks aimed especially at improving the sector. Machine learning can now provide more powerful answers than ever before. Coming to the conclusion, as the deep learning technology advances, it's important to know the dimensions and techniques for monitoring deep learning hardware and software, representation, relevance and equity, repeatability, affordability, cost, and scalability and openness are being benchmark concepts. CPUs, GPUs, FPGAs, and ASICs are the most common deep learning hardware architectures. Machine learning platform were addressed as well as methods to improve the performance. We have included a list of 11 quantitative benchmarks parameters to help you compare deep learning hardware. In compared many of non-AI algorithms that are frequently faced in reality, AI algorithms benefits from many core systems and high bandwidth memory. As a result, it is only the computational ability of hardware that makes it more or less suitable for AI applications. Yep. Thank you.
Thank you.